Hello and welcome to Lecture 26. Today we're going to talk about something called secondary images. These are images formed from other images. This is very much building on all the lectures where we talked about image formation. Those would be lectures 23, 24, and 25. So 23 and 25, those are the big three lectures that introduced images. We had images formed by refraction, mirrors, and thin lenses. And this is the culmination of those ideas because now we're going to combine refractive surfaces with mirrors, mirrors with lenses, lenses with other lenses. That's what this lecture is very much about. It builds on those ideas. So watch lectures 23 through 25 before you take a look at this lecture, lecture 26. This is also the penultimate lecture on all of optics. This concludes our module on light, and we'll be moving on to other topics in modern physics in this lecture series. So the thing to consider is that we're really wrapping up these ideas, and that's why this has a lot of building blocks that have got us up to this point. But with that introduction out of the way, let's talk about our objectives, because we have a pretty simple objective here to talk about secondary images. We want to understand how an image formed by one curved refracting surface, mirror, or lens, so the three cases of image formation, can be treated as the object for a second curved refracting surface, mirror, or lens on the same optical axis. Okay, so the idea is we treat one image as the object for the next device, whatever it may be, mirror, for example, and then that next device is going to create an image from that previous image that we treated, yep, as an object. Okay, so it's just a two-step process. We're going to learn that problems involving inline, that just means on the same optical axis, combinations of refracting surfaces, mirrors and lenses, can be solved by using the appropriate image formula twice. That's all there is to it. Okay, now we basically have 1.5 image formulas because we've been able to use a lot of the same ideas through the 3 different cases of image formation. But we're going to summarize that here after getting our one key term, which is in the title, secondary image, defined and out of the way. Okay, so let's do that. What is a secondary image? Well, I think you have a decent idea already, but let's put it in writing. It is the image formed from an image. Okay, so on lens, mirror, or refracting surfaces can form an image that then a second lens, mirror, or refracting surface treats as an object for the purpose of forming a secondary image. Okay, so that's what a secondary image is. A secondary image can be formed from a real or virtual primary image. So now we're calling the image that was always just the image, we're calling it the primary image to differentiate it from the secondary image. And then the next one can be real or virtual itself, the secondary image. Okay, so we can have all different combinations of cases. Some are more likely than others. We can have a virtual image become a real image. We can have a real image become a virtual image. And I will show you examples of those. And we want to note that sometimes secondary images do not form or require a screen to redirect convergent rays. So in other words, there's certain cases that are less real life than others where we have to make some assumptions or say that there's something else happening to make sure that that secondary image is formed. Because in certain cases, the light that formed the primary image is not going to interact with the next optical device, the mirror or whatever it may be, because it's going in the wrong direction. And so we might just have to say that, oh, well, those light rays get redirected because there's a perfectly reflective screen, essentially a mirror with no distance between the original image and that mirror, right? A planar mirror at least. So that that's kind of one of the ideas, and it just makes some of these problems a little bit more real life or a little bit less real life than others, and I'll call attention to those. All right, so that's it for our key terms. Not heavy on the terms here. Again, this is just combining a few ideas from previous lectures that were heavy on key terms. We just want to get into our formulas. And also, these formulas are not new, right? These are not new formulas at all. These are formulas from previous lectures. This first formula was introduced in lecture 23, all right? And this was for refraction. This was image formation by refraction, all right? This next equation is image formation from mirrors, which was lecture 24, and lenses, specifically thin lenses. So that was 24 and 25, right? So that's where these two equations come from. So I just put them in here because these are the only equations we're going to be using. Again, no new equations. All right, and these are all variables that have been defined before, but we're going to define them for convenience again in this lecture. So S is the distance to the object, okay? That's in this case, and that again, since this whole equation here, this whole line represents refractive surfaces, that would be the object that's going to be refracted either within or outside the refracting surface, okay? N1 is the index of refraction on the same side as object S, okay? So, so if your object is within the refracting material, then N1 would be the refracting material. If it's outside of it, then N1 is the fluid or material that surrounds the refracting material, okay? N2, on the other hand, is the index of refraction on the opposite side as object S, okay? And notice that here I'm really focused on the idea, same side, opposite side. And I think in this lecture in particular, I'm just sticking to those terms. Obviously, we've defined all the sign conventions for images and these equations in previous lectures. And sometimes it was left and right, but it was usually same side of S, opposite side of S. Here, you'll see everything is defined as same side as S, that's object S, or opposite object S. So there's a lot of clarity there in using one definition for all of our equations. All right. What else do we have? Well, we have S prime, which is the distance to the image. And then we have R, which is the radius of the refracting surface curvature. That's because if it's planar, then then this term over here just is we have 0. Okay, it would just be equal to 0. So R can be 0 for the planar case. We're always going to have circular curvature cases, so R will always be non-zero. And then we've got magnification right over here. All right, so this is magnification for images formed by refractive surfaces. All right, and magnification here is specifically dependent on the indices of refraction, but magnification by definition is always image height, which is h prime, over object height, h. That's the magnification factor. Dimensionless, just a factor. All right, here is the table of what magnification means. If it's positive, that means the image is upright and virtual. If it's negative, it's inverted and real. All right, and then if it's greater or less than 0, it's smaller. If it's greater than or less than 1, excuse me, then it's smaller than the object. If the value of m is greater than 1, then the image is larger than the object. Okay, now this always applies to images, no matter how they're formed. But it only always applies to primary images. And I say that because there was a big rule here that if you have a positive magnification, that tells you that your image is upright. That's true, okay, and it's virtual. That's also true, but only for primary images. Because if you think about it, what does upright mean? It means it wasn't inverted. So if your image is an image, then upright might mean it just stays upside down. If your primary image was upside down. And if you have a positive magnification, sometimes now we can have upright real images in the case of these secondary images, because we can invert it twice and get back to upright. Okay, so you'll see that there are variations on this, but this always holds between one object and its image. We just have to apply it 2 times in a row subsequently, which is why we get kind of almost what seems like rule-breaking cases, but they're not. It's just the same rule applied twice. This will make more sense once you see it in the examples. Okay, but again, this is our definition of magnification. Okay, so of course then we have this equation here, the equation for mirrors and thin lenses. And not too much new to identify here, because we still just have S for the object, S prime for the image. The only thing that's new, of course, is the focal point, because refracting surfaces have no defined focal point. They only have a radius of curvature. Mirrors have both a radius of curvature and a defined focal point. And then lenses have 2 radiuses of curvature and a defined focal point. Okay, but the thing is that mirrors and lenses always have a focal point. And then here our magnification is just going to be S prime over S, not considering the indices of refraction, because in the case of thin lenses, we don't care about the index of refraction because the lens is so thin. We've eliminated the need to worry about that. So you can really think of the case of images formed by refraction as the most complicated case, which is probably no surprise because this equation is, after all, longer, but it's because it's the only case where we have to actually worry about the indices of the refraction. Okay? And here is a table to summarize all the images, okay? So on our vertical axis here on our table, we have optical variables, S prime, focal length, and radius, all right? Over here on the horizontal axis of our table, we have cases where the variable is on the same side as the object S, and cases where the variable is on the opposite side as the object S. That's either the opposite side of the mirror, or the opposite side of the refracting surface, or the opposite side of the lens, whatever it may be. It's just the opposite side, okay? And we can see all the sign conventions, right? So for example, for the same side, for refraction, S prime is negative if it's on the same side. For mirrors, it's positive if it's on the same side. Lenses, opposite, Okay, so it summarizes all those cases. For the case of the focal length, there is no defined focal length for refraction, which is why we have non-applicable in this cell of our table. But we can see that for mirrors, we have positive again if it's on the same side, but for lenses, it's negative if it's on the same side. And then finally, looking at the radius, we see that for refraction, same side is negative. Mirrors, always being the exception, same side is positive. Lenses, like refracting surfaces, have radii that are defined as negative if they're on the same side as the object S. And then all the cases where we're on the opposite side, which is always just going to be switch the sign. All positives become negatives, and all negatives become positives. Okay? And again, you can really tell that mirrors are the exception. There's a lot more of connection between the rules in terms of refracting surfaces and lenses, which kind of makes sense because after all, lenses do use refraction to form images. They just use it without considering the index of refraction. Okay? But then you might wonder what this little asterisk symbol is here in pink. Well, that's just pointing out that in the case of the radius for lenses, well, there's not a single radius. And notice the radius for lenses does not show up here at all in our equations. That's because in terms of key equations or key formulas, I decided to not include the lens maker formula, but I did include it over here because although I will not have any examples in these notes that require us to find the focal length of a lens, that could be something that could be asked. You might be given the two radii, let me zoom in on this a bit, the two radii of a lens, either a converging or diverging lens, and then have to find the focal length of that lens, and then proceed with maybe finding a secondary image formed by that lens combined with something else like a mirror or another lens. All right, and this is the note here just says the radius for lenses applies to the lens maker formula only with that. Okay, so that's the only time that we would worry about the radius of a lens, and you will not see it again in this lecture. All right, so the last thing before we get onto our examples is I just decided to show some of these sign conventions actually applied to these cases. So these are some of the cases that are similar to cases that we're going to see. So here we have a converging lens combined with a concave mirror. Here we have a convex refracting surface combined with a converging lens. And here we have a converging lens combined with a diverging lens. These are all going to be cases where there is a primary image and a secondary image. Okay, well, let's take a look at what the variables will look like. Okay, so for the first case, the mirror has a focal length that is greater than 0 because it's a concave mirror. All right, the lens here is a converging lens, so it also has a focal length that's defined as greater than 0. All right, and then we can look at all of our values of object distance and image distance. And here I'm just kind of estimating where the images would form. I'm sort of like using the image formula behind the scenes to show that in the case of the object here, all right, we have the object. The mirror is going to form an image of that object somewhere right around here. So this is the image formed by the mirror. This is defined as a positive image because it's on the same side as the focal length of the object, and that's the rule for mirrors. All right. On the other hand, for the converging lens, we see that this is the object distance to the lens, all right? And that means that our image distance for the lens is going to be this. This is S prime lens, the image, okay? The primary image. And this is a virtual primary image because it's formed on the same side as the object. And for lenses, or for converging lenses or diverging lenses, for any lens, if you have a image that's on the same side as the object, that's negative. So you have a good example of a image being on the same side of the object in both cases, but having different signs because of the different optical devices. And then finally, since we are after all talking about secondary images, we'll show a case of a secondary image because here the real image formed by the concave mirror is going to act like an object for the converging lens, just like the original object acted like an object. So we have a new object distance, which I call S lens 2, and then S lens 2 is going to form a image, in this case, an image on the opposite side of the lens. So would this image be greater than or less than 0? Would this image length be? Well, of course, it would be greater than 0 because this would be a real image, a real secondary image, all right, formed by a real primary image. All right, let's do another one real fast. All right, here we have a refracting surface combined with, again, with a converging lens. In this case, the radius of refraction is greater than 0 because it's opposite the object, because the radius would be over here. So we can actually see where is that vector located, that distance vector? Well, it's located on the opposite side of the interface between the refracting material and the surrounding fluid, thus it's opposite side. Even though the radius points towards the object, the pointing direction doesn't matter. It just matters that it's actually located over here on the opposite side. Since it's a converging lens, the focal length over here is also greater than 0. All right. And then here we see cases of where the image is going to get created. In this case, since the object is outside the focal length of the converging lens, the primary image from the converging lens is real. As far as the image created by the refraction, by the refracting surface, that's very much going to depend on the values of N2 and N1. Notice N2 is within the material because that's not where the object is located. N1 is where the object is located, so it would be the fluid over here. All right. And so those, depending on what those values are and how different they are from each other, we could have either real or virtual images formed from the refraction. But in this case, I'm assuming that maybe this is air around here and glass over here. So in that case, you would get a real image formed within the refracting material. Then that real image, which would be inverted, of course, that forms within the refracting material would act as the object for the converging lens, and that would then form another real image over here. All right, but closer to the focal point because the image acting as the object for the converging lens and the secondary image formed, well, it's much further away. And here's another case. In this case, we have a converging lens with a focal length greater than 0, a diverging lens with a focal length less than 0. We have image formation from the converging lens over here, so S prime conv for the image created by the converging lens. That's going to act as the object for the diverging lens. So then the object distance to the diverging lens is just where that image was formed, that real inverted image. And then that's going to form a virtual image that's on the same side. So it would be less than 0 and virtual. And it's just going to be a further shrunk down image that's going to be inverted but virtual because it got inverted when it was real the first time. Then the virtual image that forms just stays upright relative to how it started, so it stays inverted even though it's virtual. Okay, so those are all cases, and there's a lot of information to take in there. If they didn't make sense, that's the purpose of the examples that are just about to come. Because what I really hope to show with these practice problems, these examples of 4 types, is just what are the actual steps in solving these problems, so you get used to how to do these problems. All right. So I decided to divide them into 4 types, and these are going to be there's going to be 1 example to each type because they are fairly long examples. Type 1 are problems that involve the secondary image formed by a curved refracting surface and a mirror. Type 2, problems that involve a secondary image formed by a curved refracting surface and a lens. Type 3 is secondary image formed by a mirror and a lens. And then type 4 is image formed by lens and a lens. Notice we don't have mirror and mirror. That doesn't work particularly well. There are some cases, but I decided to just focus on maybe the cases that are cleaner and work in more applications with more variation. All right, so let's start with the refracting surface and a mirror. Okay, so here we have it. Let me read the problem statement, the example statement. An object with a height of 14 centimeters is placed a distance of S1 equals 15 centimeters in front of a concave mirror with a focal length of 13.5 centimeters. And this is pretty much drawn to scale. A convex refracting surface is located at a distance of 1 meter in front of the mirror as shown. The refracting surface has a radius of 22 centimeters, right? And that would be this distance here to get to the center, and an index of refraction of 1.45. The mirror and refracting surface are surrounded by air, which means that N1 is just going to be 1. A, where will the refracting surface form a secondary image from the image created by the mirror? What is the magnification and type of this image? And then in B, we're going to go the other way and say, where will the mirror form a secondary image from the image created by the refracting surface? All right, so we'll have 2 cases of secondary images depending on where we start. And what is the magnification and type of this image in part B? So, well, let's look at part A, the secondary image formed by the refracting surface. All right. Well, here we really want to consider all of our variables. It's so important. No matter how you label your variables, and I'll label them different ways in different problems, you want to make sure that you just have a clean labeling system for all of your variables. All right. So, of course, I have my original object distance, I'm going to have my original image distance, then I'm going to have my secondary object distance, which is just my image distance to my new interface, and then I'm going to have my secondary image distance. You can see that the first image that's formed is a real inverted image, and then the secondary image that's formed is a virtual inverted image, okay? All right, let's see how that works out. So we're going to use the image formula for mirrors with a focal length less than 0, all right? Okay, so because here we have a concave mirror, okay? So we're going to set this up and go ahead and plug in our values, all right? And let's see. So, oh, I see. I do have a small typo here because I was thinking, wait, it should only be less than 0 if it's on the opposite side, and the opposite side of the mirror is going to be for convex mirrors. And this isn't a convex mirror. This is a concave mirror. So this is just a simple typo here. I think I meant to write greater than 0, and for some reason I wrote less than 0. I just wrote the wrong thing. And you can see here I correctly do have the sign of the focal length for our concave mirror to be positive, because focal lengths of concave mirrors are positive. So please excuse this typo. I will fix this in a version of the notes if you see a further version of this notes. But again, this should be greater than 0. See, it's positive 13.5. Okay, there's our object distance, and so there is our image distance. Okay, so that's S prime mirror, all right, which is S1 prime. These are the same thing. Okay, they're equal to each other. And it's rather large, all right? It's greater than L, which is 1 meter, which means that the image, that real inverted image, forms within the refracting surface, S1 prime, okay? And the magnification of this real image formed by the concave mirror is the following. So this is how we find it, negative S1 prime over S1. So it's going to be negative 135 centimeters over 15 centimeters, or negative 9. So it's 9 times taller and flipped upside down. And now we can find the secondary image formed by refraction. We're all set up and ready to go. All we need to do is just stop thinking of this as an image and start thinking of it as an object. Okay, so we'll go ahead then and use our formula for image formation by refracting surfaces. Okay, now we want to go ahead and solve this for S2 prime. And if I want to solve this for S2 prime, the best way to do that is because I'm not going to show the step here, so I'm going to show you before we proceed. So first I'm going to subtract a term from both sides, okay? I'm just going to subtract that N1 term from both sides, okay? Then I'm going to take the reciprocal of both sides, so I'm just going to raise both sides to the power of negative 1. When I do that, then I'm going to obviously on the left-hand side get S2 prime over N2. So then when I cross multiply and get my S2 prime by itself, I'll get that S2 prime, all right, equals N2 times that difference raised to the negative 1 power, right? Because you already saw that when I started to isolate it, I ended up with this term minus this term, right? Which you can clearly see within the parentheses, all raised to the negative 1 power. And over here, I point out that N1 is going to be 1.45 because the object is within the refracting surface. And N1 is always the index of refraction that's on the same side as S. Well, S is over here, because S1 prime is playing the role of S, remember? All right, then N2 is the index of refraction opposite, so that's just the surrounding air. R is negative 22 centimeters. Why? Because it's on the same side as S, okay? Then, all right, because you can see, look, S2, all right, S2 is over here. R is on the same side as S2, okay, so it's a negative radius. And then we can find S2 by just taking S1 prime, subtracting L, see, because S1 prime, I said S2 prime, but S1 prime, subtract L, that gives us S2, which of course is just 35 centimeters, okay? So I think we're ready to plug in our numbers. So here, I've just plugged in all the numbers I already specified, all right, including that leading one, which is, of course, N2, and we get negative 47.7. So the fact that we got a negative value of S2 prime tells us that S2 prime must be on the same side as S1, all right, or S2, okay, which was kind of formerly S1 prime minus L. But anyway, so that the image is on the same side as the object. That's what negative means in the case of refracting surfaces. The image is on the same side. That's why I drew it over here on the same side, which means within the refracting material. Okay, it's further away. It got, pushed, that virtual image got pushed further in the refracting material. That's where it would appear to an observer, looking over here. Okay, so then we can go ahead and find the magnification, M2, all right, and that's just going to be negative S2 prime over S2, all right, which gives us 1.36. So it got bigger, right? That's why I draw S2 prime is a little bit bigger than S1 prime, All right, so the image got magnified when it got created as a virtual image. All right, and the fact that it's positive means it's upright, or it's upright relative to the object. But of course, the object was inverted, so it just stays inverted. Okay, so then we get an inverted virtual secondary image. Okay, and the total magnification is the product of the individual magnifications. Because whatever was the magnification on the primary image, then when we want to find the magnification on the secondary image, we just multiply the two to get the total magnification. That's always the case. All right, and you can see it because if I create something that's 9 times taller here, and I create something that is 1.36 times taller than that, then it's just going to be 1.36 times 9 compared to the original object. All right, because that's what the total magnification is, the magnification of the secondary image compared to the original object, which is negative 12.3 because it is inverted after all, and it's about 12.5 times taller. Okay, so now let's do it in another case, in the case of B, where we're going to consider the image formed by refraction first. Okay, so let's take a look at that, part B. All right, so let me use the same picture, but here, check out what's going to happen. I'm going to consider S1 prime as that first, real image formed by refraction deep inside the refracting material. And that's because now my object distance is this, okay? Now, this is then going to act as the primary image and secondary object that's going to create the secondary image. So my S2, my distance from what now is playing the role of the object for the mirror, is really far, right? I have to go all the way over here, but then that's going to create a new image that's going to show up basically right at the focal point, okay? All right. And I think at some reason I called that S2 prime. Let's see, so we have, oh, right. And it is S2 prime because it's relative to the surface of the refracting material. All right, so S, because this is the image that's being formed is going to be relative to, yeah, so, yep, so you can see that labeling there, okay? All right. Okay, so in this case, we have S1 prime, all right? And this is just our formula here that I already talked about algebraically solving for that. And I'm just doing this first because we're finding the image from refraction first. Okay, so for the primary image, all right, and now look what's going on. Now N1 is 1, right? Instead of N1 being 1.45, they've switched roles because, of course, now our object is outside the refracting material, whereas before our effective object was within the refracting material. All right, and now look, the radius is positive because it's opposite the object, because now this is our object. Okay, so those are the sort of things you have to keep track of in these problems. All right, so then S1 is just going to be 100 minus 15. So that's S1 right here, which is 85 centimeters. All right, so then I can go ahead and find S1 prime, 167 centimeters. That's how far it forms within the refracting material. All right, and then the magnification is just going to be negative 1.96. So it's taller and inverted because it's a real image. Okay, so now we can go on to the secondary image step. So the secondary image of the mirror will have S2 equals L plus S1 prime. All right, so that's this really long S2. All right, and then we can go ahead and find S2 prime, and we find that it's 14.2 centimeters. Oh, I see. I knew something did not look correct, and I see my mistake now. For some reason, I drew S2 prime relative to the refracting material, but after all, the secondary image is created by the mirror, so S2 prime has to be drawn relative to the mirror. So S2 prime should be right here, and this is another thing I'll have to fix. This is S2 prime, not this. S2 prime is short, as we can clearly see, and it should be comparable to the focal length of the lens, which indeed it is. Because whenever you have an object that's very far away from a concave mirror, the image formed by that concave mirror is going to be very near the focal point. Closer and closer, the further and further it is. And of course, our object distance for the secondary image is really far away because it's way within the refracting material. So that's why we have that secondary image being formed so close to the focal point of the concave mirror. So 14.2, okay. All right, positive because it's on the same side due to the sign convention of mirrors. All right, so again, I will fix the correct labeling of S2 prime. Okay, all right, and we want a magnification as well. So then we have that M2 is going to be negative 0.053. So it's shrunk down quite a bit, and we already know what M1 is. So then our total magnification is just the product of those two magnifications, and it ends up being a positive value. So we get 0.105, which tells us that our final secondary image is about 1/10 the height of the original object, and they are really this close to each other. The original object was, a little bit further outside the focal length. The final image, the final secondary image, is just a tiny ways outside of the focal point. All right, so they're kind of almost right on top of each other, with that secondary image being that much shorter. Okay. All right, and let's see, did I say no, I did not say the image type. Okay. All right, let's finally move on to another example. Okay, so there's our combining a mirror with a refracting surface. Let's combine a converging lens with a refracting surface. Not that it has to be converging, just a lens. In this case, I chose the converging one. All right, so in this case, we're going to have our index of refraction and A, which is the one near the object. Here I'm using A instead of 1. And B is the index of refraction on the opposite side of the object, at least, the primary object. And here are some of the variables that we're going to use. I'll just go through this one. It's got a lot of similarities to the last one. But let's see what we're asking here, because I'm not asking as much. So, I give you the details here. I give you the height, right? I give the distance of 13.6 centimeters from the thin lens. That's just the distance to the object. And a distance of 27.1 centimeters from a spherical diamond refracting rod. All right. That's why it has such a high index of refraction. All right. So I gave you these two distances. So you can sum those up to find L, which is more typically given. All right. The thin lens is a converging lens with a focal length of 5.9 centimeters. The refracting rod has a radius of curvature of 17.5 centimeters and an index of refraction of n.4 or 2.42, n equals 2.42, typical for diamond. The rod and lens are surrounded by air, which is why we have an Na of 1. What is the distance between the image formed directly by the lens and the secondary image formed by the lens of the image formed by the refracting rod? What is the size difference between the two images? And we assume that a screen exists inside the refracting rod at the location of the image formed inside in it that redirects the rays back towards the lens. And that would have been true of part B of example 1, because when we form that real image within the refracting material, that means that all those rays, those convergent rays, are just going to continue towards the left. So we need some way to send them back towards the converging lens to get that secondary image. But in this case, notice what we're doing here. We're comparing the secondary image formed by the lens with the primary image. So what is the distance between the image formed directly, that's the primary, by the lens, and the secondary image formed by the lens? So we're not going to compare between secondary images. We're going to compare between a primary image and a secondary image. But of course, we'll need to consider two primary images in that case, because we'll need to consider the primary image formed by the refracting surface in order to get the secondary image. And since we need to compare, we're going to consider the primary image formed by the converging lens as well. So that means we have a few more variables than we did in either part A or part B alone in the previous example. All right, so let's define some of those, right? Because you can see a lot of them in the picture. So we'll define the image created by the lens directly as S1 prime, the image created by the refracting rod as S double prime, and the image created by the lens resolving S double prime as S2 prime. Okay, so let's just jump right into the solution here. All right, so first the direct image. That's the direct image formed by the converging lens. All right, so there's our formula for image creation by a lens, solve for S1 prime, and plug in our numbers, and then we get 10.4. So I found that S1 prime is 10.4, about twice the focal length, right? Because we found the focal length was 5.9, so pretty much draw on the scale over here. All right, and that would be a real image, real and inverted, something like that. Okay. All right, and would it be smaller? Yeah, and it would be about half the height of the object. Okay. And now the refractive image. Okay, so this is the primary image formed by refraction. That's also going to be a real image, and it's going to form over here at S double prime. Okay, so here we're going to set up the formula for image formation by refraction, solve for S double prime, which is just the image distance relative to the refracting surface, plug in our appropriate indices of refraction and our radii, including the fact that the radius is positive, and we get 54.7 centimeters. So about just scale over there, about twice the radius, okay? And finally, the lens's image of the refractive image. Okay, so now our object distance is this S right here, because S is going to be the sum of S double prime and the distance between the refracting surface and the converging lens, which is just S2 plus S1. All right, so then you can see that S is S double prime plus S2 plus S1, and it ends up being 95.4 centimeters, okay? And so now I can use that information, including the focal length of the converging lens, to solve for S2 prime. All right, and there we get 6.29 centimeters. All right, that makes sense because as the object, all right, because this is our object in this case. As this object gets further and further away from the converging lens, where does the image start to get closer and closer to? The focal point of the converging lens. And indeed, this is pretty close to the focal length of 5.9 centimeters. All right, and so we were asked to compare between them. So then the difference between the image distances, 10.4 centimeters minus 6.29 centimeters, is 4.13. All right, so that's this distance right here. That is our delta S. See? All right. And I should probably call that delta S prime because they're images after all, but I obviously just called it delta S. All right, and then we can compare our magnification, so we can find the magnification of the primary image. So that gives us a H1, and this is the primary image formed by the lens, that the one that we never cared about a secondary image for. So that gives us a height of 7.66 centimeters, and then we can go ahead and find M2, which is going to be a total magnification. So it involves two steps. That's the magnification formed by refraction multiplied by the magnification formed by the thin lens, treating that image as its object. And so that gives us a total magnification of 0.0959, or a height of 0.959 centimeters. So we have one that's pretty tall, one that's quite shrunk. So that gives us a height difference of 6.7 centimeters. Right? Because again, one is very short, the other is quite tall. Okay, of the two images that are formed. And as far as the image types, they're both going to be real images. All right, so we have two real images that are being formed, and one is going to be a real upright image because it got flipped twice. That's the really short one. That's the one that ends up being only 1 centimeter tall. And then we have the one that was just formed by the refraction of the thin lens, and that one is going to be an inverted real image, and that one is actually fairly tall, right? 7.66 centimeters. And what was the original height? 7.1. So that one slightly shrunk, but not very much. Okay, so there's a case of comparing between images in hopefully a meaningful way. And we're going to do something really similar in our third example, our third of 4 examples. All right, but we're done with refracting surfaces. Now we're just going to look at mirrors and lenses. All right, so an object has a height of 5 centimeters. It is placed 30 centimeters from a concave mirror as shown. Right, so that distance is 30 centimeters. All right, the mirror has a focal length of 10 centimeters. There's our focal length, right? That gets us to the focal point. All right, and it's located to the left of the object. To the right of the object is a converging lens with a focal length of 15 centimeters, which is located 21 centimeters from the object. The object's base is located on the optical axis of both the mirror and the lens. The lens forms two images, one directly from the light from the object and another secondary image from the reflective image of the mirror. What is the distance between the two images, and what is the type and magnification of each? So again here, just like in the previous example, we're going to be comparing between a primary image formed by the converging lens and a secondary image formed by the converging lens. All right, so real similar idea there. Another thing to consider here is that this example is a little bit cleaner than the previous one because we don't have to redirect our rays. Our rays are going to be naturally redirected, and I'm actually going to show a ray diagram. In the previous two examples, I showed all the relevant lengths like S1 and S1 prime and S2 and S2 prime, or whatever labels I might use. But here we're actually going to, I'm going to show you a ray diagram to just further elucidate this idea. Okay, so let's go ahead and start comparing our images. All right. So here is our ray diagram and all of our relevant measurements. And yes, this is a rather busy figure with everything going in here. And I have the principal rays color-coded, right? So we have our 3 principal rays coming from the original object. That's going to form a real inverted image due to the concave mirror, all right? So there's the first real image from reflection. Now that real image from reflection, you can see the rays are continuing off, and they're going to then obviously interact with the converging lens. And so then those are then going to form a secondary real image from refraction of the reflected real image, right? So here's our secondary image. Again, real, upright and real because it got flipped twice, okay? Just like in the previous example, but again here, the rays got naturally bounced back towards the converging lens. So this is a real case where there definitely would be an image formed there. But of course, that's not the only image that is being formed by the converging lens. And it's not the only real image formed by the converging lens, because the object, in addition to sending rays off to the left, the ones that interact with the mirror, sends rays off to the right that are going to directly go through the thin lens and get focused at a single point, creating the first real image from refraction. And refraction here don't think refracting surface, think lens, because after all, lenses do function based on the law of refraction, okay? Just a simplified version of it, okay? And then we've got all the relevant measurements, like the object distance for refraction, the image distance for reflection, the second object distance for refraction, and then the images, the second image, the first image, and the distance between the images. Okay, so yes, it is busy, but I hope that makes everything clear in terms of the labels. All right, so now let's actually get to the math using the image formula. All right, so using the thin lens formula for images, we're then going to find the first reflected image, right? That's this one. Or no, sorry, the first reflected image is this one. All right. All right. So, and I call it the thin lens formula, but obviously we're using it for a mirror first, but that's, it's the same formula. Okay. So here we see that we're going to find the reflective image. That, again, that's this one. All right. And this is the focal length of the mirror we're going to use in this case. So MIR for mirror. We'll zoom in a tad on that. All right, so let's go ahead and plug in our numbers, solve for our image distance, while noting that our focal length is defined as positive because it is a concave mirror. And so then we're going to go ahead and find our image distance relative to the mirror, and we get 15 centimeters. Very good. All right, so that's this value right here. Okay, so now we can go on to find our first refracted image. That's this one. Okay, all right, this large magnified one. Okay, we'll go ahead and consider the focal length of the lens in this case. All right, so there we have it. In terms of plugging in the numbers, solve for that image distance, S first prime. All right, that's this one. Okay, notice again that the focal length is positive because it's converging lens, and the value we get is 52.5, right? Which is, so yeah, it's definitely further away from the focal point, and that's why we have that positive magnification, or at least that greater than 1 magnification. Okay, and so we can kind of see everything together. I zoomed out a bit, but let's get on to our second refracted image. Okay, so that's where we're going to use SRAC2 for our object distance. Okay, and then we're going to find S second prime, and we're going to use the focal length of the lens because this, after all, is an image formed by the lens. All right, and notice that SRAC2 is L minus S prime ref. All right, so it's because this is where the image was formed from the mirror, and then if I want to find the distance of that image to the lens, I just take L and subtract that image distance. Okay, and we were told L, so we can definitely figure that out. L was 51. The image distance that we found previously was 15. All right, so that's going to be our SRAC2 is 51 minus 15 centimeters. All right, and notice that again we have a positive focal length because it's a converging lens. All right, so then we'll find that image distance for the secondary image, and what do we get? 25.7. All right, so indeed it's much closer to the focal point, not as magnified. Okay, so now we can finally compare the two. So in the distance between the two images, which is S first prime minus S second prime, because after all, S first prime was the one that was further away, had a larger value, is 26.8 centimeters. And that was just 52.5 minus 25.7. Okay, so there's a distance between our two images. What type of images are these? They're both real, but one is real and inverted and one is real and upright. Okay, so you could put a piece of photoactive paper there and actually get a actual image to form in both cases. What about the magnifications? Okay, well, why am I asking about magnifications? Because in part B, I say what is the type and magnification of each image. All right, well, in this case, we'll consider all three images. Okay, so the reflected one has a magnification of negative 0.714. It was real and inverted. The first refracted one, the first one created by the lens, has a magnification of negative 2.5. It is also real and inverted. And then the magnification of the second refracted one, well, to compare it to the original object, we'd want to have a total magnification. We could compare it to the image formed by reflection if we wanted to, but it makes more sense to compare it to the original object. And that's something that should always be specified. All right. And so in that case, we just have the product of the two magnifications. We take everything together, which cancels out the negative. So that means we end up with a real upright. And the fact that it's positive tells us it's upright. And indeed, but it's still real because there's actual converging rays there. Okay. So there's all of our images all compared. All right. So let's do our final example. And do note that we didn't end up actually using the height here. We just only compared magnification values. All right, so it didn't really matter. Oh, there it is. We didn't really matter that it was 5 centimeters tall. It could have been just a height h. Okay, so here is our last case combining two lenses, a diverging lens with a converging lens. Like the previous example, example 3, this one's very clean in that this is a case where we don't have to worry about redirecting any rays. We have images that are going to form very naturally. This would be a very real life example. So a pair of thin lenses are shown that both have focal lengths of absolute value, f equals 23.7 centimeters. I say absolute value because, of course, the diverging one is going to be negative 23.7 centimeters, and the converging lens is going to be positive 23.7 centimeters. An object with a height of 18.5 centimeters, this time we'll use that, is located at a distance of 44.3 centimeters to the left of the diverging lens. All right, that's this distance, sorry, S1. All right, and the distance between the lenses is 82.9 centimeters. That's L. All right, so part A, where will the secondary image formed by the converging lens be located relative to the converging lens? So in this case, we just care about a single secondary image. Okay, so let's use the lens formula twice and get there. All right. In many ways, this is probably the simplest of all the examples, a good one to end on. All right, so there's that H. We'll end up using that down the line. All right, so let's do a ray diagram here, right? With no variation on the rays. We'll make this a little bit less technicolor, a little bit less rainbow. We just have 3 primary rays. These are the primary rays, following the rules for a diverging lens, which involves our cases of continuing projections of rays that would go to the focal point, or a projection of a ray that would have come from the focal point. That's these tight dashed lines. And then if we consider the 3 diverging rays, and then we project them back, then we end up with the actual location of the primary image, which is this larger space dashed line represents the projection of this particular divergent ray back in. And we actually don't really need to draw the projection of these 2 divergent rays because they just overlap on the lines already drawn. But regardless, where all 3 projections of diverging rays overlap is our primary image location, which is a virtual upright image. Okay, so that's going to be our primary image. However, that primary image will act as an object for the converging lens. It doesn't matter that it's virtual because all the rays seem to be emanating from there. So what's going to happen is these rays, once they get to the converging mirror, they're going to get refocused. Okay, so we'll treat this as our object. We'll consider the principal rays, the ones that go through the focal point and then run parallel and pass through the focal point. That's going to create a real image, a secondary image. All right, so it's going to take a virtual image and turn it back to real, which is pretty neat. We haven't actually seen that, but it certainly is possible. And here's a case of it happening. Okay. All right, here are all of our variables, S1 prime, S1, all right, S2, and S2 prime. All right, so our 2 object distances and our 2 image distances, and that's all we'll need for the problem. Okay, so first we'll find the virtual image formed by the extension of the divergent rays. That's the primary image. Okay, so here is our image formula. Let's go ahead and solve for S1 prime. Make sure to plug in our focal length as negative because it's for the diverging lens. Plug in the appropriate object distance, and we get negative 15.4. Just as we expect, it's within the focal length, and it's closer and shrunk down, all right? Which is always the case when you have an object outside the focal length of a diverging lens, okay? All right, images are always shrunk in diverging lens, but they end up inside the focal point if the object started outside. And they end up inside the focal point if the object started inside, but then they also are closer to the object. All right, so now then we will find the distance of this virtual image to the converging lens, okay? So that's going to be S2. And S2 is just the absolute value of S1 prime plus L, all right? Or you could think of, if you had a coordinate axis, you could define this as your x equals 0. And since you're adding a negative term, because S1 prime is on the negative side, regardless, you need to get this total distance, which is why I took the absolute value, okay? So it's just 15.4 plus 82.9, because L was 82.9 centimeters, which gives us 98.4. So almost a meter between this primary image and this diverging lens, okay? All right, so now we can go ahead and use that. So now we can find the secondary real image formed by the converging lens by taking the primary virtual image as an object, okay? And so what's happening there is the converging lens refocuses the diverging rays, right? Which all, by extrapolation appear to emanate from that point, that virtual image point, okay? So the image formula in this step is, of course, this one. And then we just solve for S2 prime. All right, plug in the appropriate values. Notice here we're plugging a positive value for the focal length because now it's the converging lens that is creating the image. All right, there's our object distance, and there is our image distance. All right, 31.2. And how does that compare to our focal length, 23.7? That makes sense because we're pretty far away. Not only about 3 focal lengths away, so we're not creating an image right on top of the focal point, but there it is, right? And it's so shrunk down because it got shrunk down twice. There wasn't much in terms of shrinking of the image to, from this step to this step. It mostly occurred from with the virtual image of the object from the diverging lens. But regardless, the overall effect is quite a bit of shrinking. Okay, but there is our final location, and we're asked for the distance relative to the converging lens, and that's what this represents, right? So 31.2 is our answer to part A. All right, it is real and inverted. Okay, good. And you might be like, wait, but that's what we'd expect from a primary image, real and inverted. Well, that's because we ended up with a virtual upright image. So then when it got flipped upside down, it just became real and inverted, right? So secondary images that are real aren't always real and upright. You see a case right here, all right? Okay, so they can be both. And finally, in part B, the total magnification. Okay, so the total magnification is the product of the individual magnifications. Each one is just our appropriate cases of either S1 or S2. All right, and so we plug in all the values that we already saw in part A, and so we get our total magnification is negative 0.111, which means then to find the final height, because we were asked here in part B, to what will be the height and type of this secondary image, and that's typo, I should say secondary. All right, let's see. Well, we just take that magnification factor, multiply by the original height of 18.5 centimeters, and we get that the image is 2 centimeters tall and upside down. There's our little real image flipped upside down. Okay, all right, well, that concludes our final example on secondary images. I hope this has been a good amount of practice, because of course the purpose of the examples was just to show you actually how this works in practice so you can solve these types of problems. Thank you so much for watching. Bye for now.